Hi, everyone. My name is George Chen, and I'm a product marketing manager for MPS. And I'm here today with Dee Han, who is the systems application manager at MPS for isolated products. Today, we'll be discussing MPS onboard charger solutions. And I would like to thank Avnet Silica for this invitation to this webinar series. And we're looking forward to continuous cooperation moving forward. Here's a quick overview of what we'll be covering on the agenda today. First, we'll review some electric vehicle subsystems. Then we'll talk about onboard charger and traction inverter block diagrams. We'll go through some of the MPS solutions for electrification. And lastly, we'll talk through a design using a resonant LLC power supply, and then we'll have a conclusion for this presentation as well. As the world strives for carbon neutrality, electric vehicles are rapidly taking market share from internal combustion vehicles. Billions of dollars are currently being invested by the top automotive OEMs worldwide in order to electrify their vehicle lineups with a mixture of both battery electric vehicles and plug-in hybrids. In 2021 alone, the number of electric vehicles sold more than doubled to greater than 8% market share, with 6.6 million EVs sold in 2021. Here we have the typical electric vehicle subsystems that are needed within an electric vehicle. Battery management systems that help manage the battery health, the state of charge, and cell balancing of the vehicle battery. There are also onboard charger and DC-DC converters. The onboard charger helps convert AC voltage into DC voltage when using an AC charger, and the DC-DC converter is used to convert the high voltage battery to either 48 volt or 12 volt for powering a vehicle subsystem. The last subsystem within an electric vehicle is a traction inverter, which converts energy from high voltage battery to drive the electric motors, as well as recuperate energy from regenerative braking. These subsystems are all very important in creating an electric vehicle. So here we take a look at a typical onboard charger block diagram. With onboard chargers, they are actually found in both plug-in hybrid vehicles as well as battery electric vehicles, and are typically rated between 11 kilowatts up to 22 kilowatts. The power level of the onboard charger determines the max charge rate of a vehicle when it is connected to an AC source. On the left-hand side of the block diagram, we have the PFC stage, which converts the AC voltage from the power grid into an intermediate DC voltage between 400 volts to 800 volts. The second stage of this is the isolated DC-DC stage that converts the intermediate DC voltage to the target voltage that is specific to the battery being charged, which is typically between 400 to 800 volts as well. These battery voltages have been increasing as it allows for higher efficiency, faster charging times, and lighter cabling within a vehicle. In order to maximize the efficiency of an onboard charger, new designs have been utilizing silicon carbide FETs to help increase the range of these onboard chargers. MPS offers both isolated gate drivers as well as transformer drivers, isolated bias supplies for biasing silicon carbide, and IGBT FETs in these designs. We'll be discussing more about these solutions later on. The next component is traction inverters. Traction inverters are used to convert DC energy from the high voltage battery to a three-phase AC energy to drive the traction inverter. They are usually operated off of a 400 volt to 800 volt high voltage battery pack with currents reaching hundreds of amps. A traction inverter typically has 6 isolated gate drivers to separate the controller domain from the high voltage AC domain. In order to optimize efficiency, there's actually an optional DC-DC that can be used, which requires 2 more isolated gate drivers in the design. Currently, most traction inverters operate between 20 kilowatts up to 200 kilowatts, depending on if this is used in a hybrid vehicle or a fully electric vehicle. Similar to an onboard charger, there's a trend to shift to silicon carbide to maximize efficiency and to increase range of electric vehicles, as the battery makes up the bulk of the cost, and OEMs are looking to maximize this range with a given battery size. Due to the high power nature of the traction inverter, gate drivers that can handle peak currents exceeding 30 amps are needed, with special protection features such as active Miller clamps and desaturation protection becoming more and more important for these designs. The next system we see here is for a DC fast charging station. This block diagram shows the conversion from a three-phase AC voltage into a 250 volt to 800 volt DC voltage that is used to charge electric vehicles. A DC fast charging station typically contains several of these subunits, which generally ranges from 30 kilowatts up to 75 kilowatts. Multiple of these subunits are put in parallel in order to achieve 250 kilowatt, 350 kilowatts, or even higher amounts of power. The DC fast charging system is generally comprised of two conversion stages as well. The first stage is a power factor correction stage, which converts the AC voltage from the power grid into an intermediate DC voltage bus between 800 volts to 1300 volts. A three-phase, three-level rectifier/inverter topology is commonly used in this PFC stage. This particular topology refers to a three-level converter that can interface with a three-phase power grid. The next stage is the DC-DC stage, where an isolated DC-DC converts the intermediate DC voltage to the target voltage that is specific to the battery being charged. LLC and phase shift full bridge converters are common topologies for the DC-DC stage. MPS offers several products such as isolated gate drivers, transformer driver bias, and isolated power modules for DC fast charging stations. Some of the biggest challenges for this application are maximizing power density, reducing cost, and reducing size. These are some of the target automotive EV and mild hybrid applications that MPS is targeting. The first is charging stations, or the infrastructure for electric vehicle, which is very important as adoption of electric vehicles keeps increasing. Within the electric vehicles themselves, we are targeting applications such as an onboard DC-DC, onboard charger, as well as traction inverters. For mild hybrid vehicles, MPS is targeting 48 volt DC-DC as well as belt start generator applications. MPS offers a number of AEC-Q 100 compliant products, including isolated gate drivers, digital signal isolators, isolated power, isolated amplifiers, as well as a half-bridge GaN driver. These products support various isolation requirements to really maximize system-level safety with 1.5 kV, 3 kV, and reinforced 5 kV isolation solutions available. Some of the products that MPS offers have switching frequencies all the way up to 10 megahertz, which can really help minimize the total solution size. For the safety certifications that we're compliant to, we are certified for UL 1577, and we have several VDE 0884, 11, and 17 certifications underway as well. This is the isolated gate driver and power supply roadmap from MPS. On the left-hand side, we have the MPQ 18913 and the MPQ 18914. These are half-bridge transformer drivers for biasing an isolated supply, and these are really used as a power supply for gate drivers. This particular device is really optimized for biasing silicon carbide and can provide multiple output voltages of 20 volts and -4 volts for biasing silicon carbide. These devices can operate at frequencies up to 10 megahertz and include automatic resonant frequency detection and are available in an AEC-Q 100 grade. On the right-hand side of this roadmap, we have our isolated gate drivers. On the top row, we have two single-channel devices, the MPQ 18811, which is a single-channel isolated gate driver with isolation of 3 kV or even up to 5 kV, depending on the package type. The next single channel product we have is the MPQ 1918. This is a 100 volt half bridge GaN driver, which is made specifically for biasing gallium nitride devices and supports a VCC voltage of 3.6 volts to 5.5 volts. This device has very low propagation delay of 10 nanoseconds and has excellent propagation delay matching of 1.5 nanoseconds as well. The last devices that MPS have on our roadmap are our dual channel gate driver family, the MPQ 18831, the MPQ 18851, and the MPQ 18871. This family of products offers several different input types, including a dual input half bridge, dual independent inputs, or a PW input half bridge as well. These devices support several different isolation rating levels from 2.5 kV to 3 kV, all the way up to 5 kV, and these are all available in an AEC-Q grade 100 with wide body samples being available in July 2022. The first device that we'll be talking about today is the MPQ18811. This is MPS's isolated single-channel gate driver. This device provides isolation all the way up to 5 kV in a SOIC wide-body package. We have excellent CMTI performance at greater than 100 kilovolts per microsecond, and this device has an output drive supply of all the way up to 30 volts with several different UVLO options available, including 5 volts, 8 volts, 10 volts, 12 volts, and 15 volts. All these different UVLO options means that this device can be used to bias several different types of FETs, including silicon FETs, silicon carbide FETs, gallium nitride, as well as IGBTs. The sink and source peak current of this device is 6 amps all the way up to 10 amps with a 40 nanosecond typical propagation delay. We do have a version within an SOIC 14 narrow body package, which has much more advanced protection features, including desaturation detection, as well as an adjustable soft turnoff and desaturation fault function. These products are made to operate with a junction temperature range of -40°C up to 150°C, and these are all AEC-Q 100 qualified. For the narrow body SOIC 8 and the narrow body SOIC 14 package, we can achieve up to 3 kV isolation, while the SOIC 8 wide body package can achieve reinforced 5 kV isolation. These devices are pin-to-pin compatible with other single-channel gate driver suppliers. The next device we have here is the MPQ18818. This is MPS's 100-volt half-bridge GaN driver. This device has a VCC range of 3.6 volts to 5.5 volts with very low 0.2 ohm and 1.2 ohm sink and source resistance. This low figure of sink and source resistance really helps optimize the efficiency for these designs. This device also supports a very fast propagation time of 20 nanoseconds with excellent 1.5 nanosecond propagation delay matching. This device does have wettable flanks and is available in a 3x3 millimeter flip chip QFN package with 1 millimeter distance for between A ground and high voltage pins. This device has higher drive capability compared to some of the competitor half-bridge GaN drivers, and the flip chip package with lower inductance helps with EMI performance. This device has also been, the pinout of this device has been optimized to achieve a better drive current loop as well. The design of the MPQ18818 GaN gate driver was made in collaboration with EPC. These devices have been made specifically for applications such as 48 volt to 14 volt bidirectional converters for mild hybrid applications. GaN FETs and GaN gate drivers provide fast switching, small size, and high efficiency to increase power density and save size and weight of 48 to 14 volt converters. An example of the efficiency curve of the MPQ18818 plus the EPC2206 can be seen on the left-hand side. Even with 270 watts of power, the efficiency can reach 95.5% with a 48 volt input, 12 volt output at 1 megahertz. The MPQ18818 has been tested with several different EPC GaN FETs, such as the EPC2206, the EPC2218, and EPC2204. Each of these devices have different RDS-ons depending on one's power and efficiency requirements. The next device we have here is the MPQ18831, 51, and 71, which is our isolated dual channel gate driver family. These 3 part numbers have different input types, including a dual input half bridge, dual independent drivers, as well as a PWM input half bridge available as well. These devices have isolation all the way up to 5 kV and has a wide driver bias range from 6.5 volts to 30 volts and several UVLO options which enable more flexibility in using different types of FETs such as IGBTs, silicon carbide, GaN, and silicon FETs. The source and sink peak current of 4 amps and 8 amps allows for usage of high power FETs with faster switching edges and higher efficiency. The 100 kilovolt per microsecond CMTI allows for faster switching without affecting signal integrity. Lastly, this device is pin-to-pin compatible with several other dual-channel isolated gate drivers, which can really help increase supply chain continuity in the current environment. This device also has a 20-second typical propagation delay spec with a very tight plus or minus 5 nanosecond distribution from part to part. The operating temperature range of this device is -40°C to 150°C junction, and this device is AEC-Q 100 qualified as well. We have 3 different packages available. There's an SOIC 16 wide body package, which can achieve a 5 kV isolation rating. There's a SOIC 16 narrow body package, which can achieve a 3 kilovolt RMS isolation rating. And then lastly, we have the LGA 13, which can achieve 2.5 kV RMS isolation. In this table here, we're comparing several different power device requirements for the gate drivers. We are comparing silicon FETs, IGBTs, silicon carbide, as well as GaN FETs. With GaN FETs, they can achieve the highest switching frequency of greater than 1 megahertz, while IGBTs, which is an older technology, has the lowest switching frequency of less than 100 kilohertz. Both silicon FETs and silicon carbide FETs have a high switching frequency, often greater than 20 kilohertz. In terms of the voltage levels, GaN is really optimized for designs that require less than 650 volts, whereas IGBTs, silicon carbide, and silicon FETs are optimized for designs that require greater than 650 or even over 1,000 volts. In terms of power levels, GaN FETs have low to medium power supporting less than 10 kilowatts, while silicon FETs can support, both silicon FETs and GaN FETs support low to medium power levels of less than 10 kilowatts, whereas both IGBTs and silicon carbide is really optimized for high power designs requiring greater than 3 kilowatts. The operating driving voltage for a silicon FET is 10 volts to 12 volts, 12 to 15 volts for an IGBT, and silicon carbide FETs often require a positive negative rail of 20 volts or higher with a negative 4 volt or so, while GaN FETs require a driving voltage of around 5 volts. This is why GaN FETs often require a UVLO level of 3 or 4 volts or lower. For negative gate drive voltage, it's highly recommended for IGBTs and needed for silicon carbide, whereas GaN and silicon FETs do not need a negative gate drive voltage. When we look at the output UVLO, this is directly related to the operating driving voltage. So for silicon FETs, they often operate with a UVLO of 5 volts or 8 volts. IGBTs generally use a UVLO of 8 volts or 10 volts, and silicon carbide requires higher UVLO levels of 12 or 15 volts or above. Because the driving voltage for a GaN FET is 5 volts, the UVLO level we need here is 3 volts. For propagation delay, GaN FETs and silicon carbide FETs both have short propagation delays, while silicon FETs generally need shorter times as well. When we're looking at IGBTs, the propagation delay spec is not as critical. Oftentimes, we see that silicon carbide is a trend in the industry for onboard chargers, charging stations, and traction inverters, while IGBTs are also used in similar applications for motor drives, servo, and legacy OBCs. There are some use cases for silicon MOSFETs as well, and GaN FETs have not yet found a home in most automotive applications. The next device we have here, this is the MPQ18913, which is a 30 volt, 0.5 amp LLC transformer driver for isolated bias supplies. This device supports an input voltage range of 5 volts to 30 volts and can survive transients all the way up to 50 volts. This device has programmable frequencies from 750 kilohertz up to 5 megahertz for the MPQ18913 and all the way up to 10 megahertz for the MPQ18914. This device comes with automatic resonant frequency detection as well as an optional spread spectrum for EMI reduction. This device can support up to 5 watt designs in a small QFN10 2mm by 2.5mm package with wettable flanks. This device is really optimized for driving IGBTs as well as a silicon carbide gate driver bias and can find use cases in EV DC fast charging stations as well as traction inverters and onboard chargers. The typical LLC transformer driver is compared against solutions such as a Flyback. Here we see a PCB footprint analysis with the MPQ18913 versus a competitor Flyback solution. As you can see here, due to the higher switching frequency achieved by the MPQ18913, this can result in much smaller BOM components in terms of the amount of input and output capacitance as well as the size of the transformer. The total solution size required for the MPQ 18913 is 109 millimeters squared, which is 40% smaller than a comparable flyback solution that requires 180 millimeters squared. We also require much less components at 21 external components versus 26 for a competitor flyback. Here we have a BOM cost analysis. When we look at the total capacitance needed in terms of high voltage and low voltage capacitors, the MPQ 18913 shows great savings of more than 20 cents with 11.6 microfarads of high voltage caps versus 4.7 microfarads for a PSR flyback. While on the low voltage capacitor side, you see great savings requiring only 2 microfarads versus greater than 64 microfarads for a flyback. In terms of the total amount of diodes between Schottky, Zener, and switching diodes, the MPQ 18913 requires 2 diodes total, while a flyback converter might require 5 diodes. Another big cost saving is made in the transformer. With the higher switching frequency, we're able to achieve a 13 microhenry transformer, which is 11 by 6 millimeters, whereas for a PSR flyback that operates at less than 400 kilohertz, it might require a 30 microhenry transformer that is 9 by 10 millimeters as well. If we look at the total BOM cost, the MPQ 18913 can achieve a 60-cent BOM cost plus the cost of the IC, while the PSR flyback converter is almost twice that at $1.10 plus the cost of the IC. This shows that with the MPQ 18913, we can achieve a BOM cost that is almost 46% lower compared to a competitor flyback. Next, let's look at the MPQ 18914 versus a competitor PSR flyback. As mentioned earlier, the MPQ 18913 and 4 can achieve a much higher switching frequency all the way up to 10 megahertz versus less than 400 kilohertz for a PSR flyback topology. The transformer is also much smaller because of this higher switching frequency. And one good thing about the MPQ 18913 is that it can actually utilize leakage inductance as part of the resonant tank, whereas leakage inductance in a flyback design can induce voltage spikes and cause extra losses. Another benefit of the MPQ 18913 and 4 is that it's much easier to achieve a higher isolation voltage while still keeping the isolation capacitance relatively low. With the MPQ 18913, we can achieve isolation voltage of up to 5 kilovolts versus PSR flybacks usually coming in at 1.5 kV or less. The EMI emissions for the MPQ 18913 is also better due to the soft switching, and we also have much smaller package size and smaller total solution size compared to a PSR flyback solution. Next, I'll be handing it off to Dee to talk about the isolated power supply for gate driver design.
Hi, this is Dee. So isolated gate drivers are key parts of the power converter activating the switches, which drive the power conversion. These gate drivers take control signal from the primary side or the low voltage side, then turns on or turns off the power switch on the secondary side or high voltage side by sourcing or sinking currents to the gate of those power switches. Of course, it provides an isolation barrier between the high voltage side and low voltage side. As we can see, the gate driver do need power sources on the secondary side, which is illustrated by VDD on this diagram. So isolated power supplies are required for the gate drive circuits. Here in the red block diagram is showing the isolated power supply. It takes the input voltage from primary side and generate the isolated output voltage on the secondary side. Obviously, an isolation barrier has to be present between the primary and secondary side inside the power supply, and that's usually provided by a transformer. In EV industry, we are seeing some interesting trends that put more requirements on the transformer design of these isolated power supplies. First of all, the battery voltage and the DC bus voltage in the electric vehicles are gradually transitioning from 400 volt to 800 volt levels in order to facilitate higher power density traction drive and boost up the overall drivetrain efficiency. But with 800 volt DC bus, we will need a transformer to withstand higher isolation voltage. Secondly, the industry is gradually shifting from silicon IGBT to silicon carbide MOSFETs in their converter designs to take advantage of the high speed and low loss features of silicon carbide devices. But on the other hand, high switching DVDT operation of silicon carbide will drive a lot more current across the isolation barrier compared to the IGBT. The noise current can potentially disturb the normal operation of the controllers and sensitive circuits on the low voltage side. So we will need isolation capacitance of the transformer to be as small as possible. Here we are showing an example. Assuming each transformer has 20 picofarad capacitance between primary and secondary side, which is very typical for an off-the-shelf transformer. And the silicon carbide MOSFET switching slew rate is assumed to be 100 volt per nanosecond. Then the common mode current across isolation boundary will be 1 amp, which can be obviously destructive. So how do we deal with the new requirement for the transformers? The first thing is the interwinding capacitance. The interwinding capacitance can be compared to a parallel plate capacitor. Since the insulation material and area of coil offer less design freedom, the best way to reduce this capacitor is by separating the two windings, which means increasing the thickness of the insulation layer. As we can see from the equation, the capacitance is inversely proportional to the distance between two winding coils. So we need to increase that distance to reduce the capacitance. Meanwhile, by increasing that distance, we also can increase the isolation distance, hence increase the isolation voltage of the transformer. However, this does come at a cost. Increasing the isolation thickness reduce the interwinding capacitance, but also worsen the magnetic coupling between the two sets of windings, which means the leakage inductance will increase. Therefore, designers will have to find a way to deal with this unavoidably large leakage inductor. One of the most frequently used topology for this application is the flyback converter. Flyback converters behave like a buck boost converter, but the inductor is split to enable isolation between the input and output. In this converter's efficiency is very closely linked to how tightly the primary and secondary inductors are coupled. The increased leakage inductance loosens the coupling, so the amount of energy which is transferred across the inductor will decrease. This will cause a large loss in efficiency and also forces the designer to select larger and more expensive component to accommodate the voltage spike created by the leakage inductor's resonance. For this reason, flyback converters are not the most ideal solution for high power designs. To illustrate a little bit more on how a flyback converter operates, when the switch turns on, the current will flow through the switch as well as the leakage inductance. Then when the switch is turned off, some power will stored in the magnetizing inductance will be transferred to the secondary, hence to the output. But the energy stored in the leakage inductance has to find a way to still, but the current in the leakage inductance still has to find a way to flow somewhere. That will cause a resonance between the leakage inductance and output capacitance of the switch, resulting in high voltage spikes across the switch. The switch node voltage spikes will increase the switching device rating, complicates snubber design, and generate losses and noises. It also limits the maximum operating frequency. Larger the leakage, worse the performance the flyback will have. New technological development have led to the adoption of LLC converters as the most efficient topology for isolated gate drive power supplies. These converters are based on a resonant LLC tank, which has a magnetizing inductor for energy transfer, as well as an additional capacitor and inductor whose purpose to make the tank resonant at a certain frequency. The converter uses this resonance to ensure high efficiency power conversion. The main benefit of the LLC converter is that the leakage inductance of the transformer can be used as the resonant inductance in the tank in eliminating the issue of efficiency loss or voltage spike that is associated with the flyback topology. This is why LLC converters are the best choice for powering isolated gate drivers. So here I'll show an design example for the isolated power supply biasing silicon carbide FETs. Here's a block diagram assuming the input voltage is coming from a 12-volt vehicle battery. Then it will go through a boost stage to 29 volts. Then this regulated 29 volts will go through our LLC converter to generate the 20 plus 20 volt and minus 4 volts. Note in this diagram, we are assuming the input 12 volt is directly battery voltage, which is unregulated and can vary a lot during low dump and cold crank. If we have a pre-regulated rail, then this boost converter won't be necessary. And in this diagram, we are using one LC IC to drive one transformer with 3 output windings, like shown on the right. But to minimize the cross-coupling between different outputs, we can also choose to use one IC to drive 3 different transformers, or we can choose to use 3 ICs to drive 3 different transformers, depending on the designer's needs. In this design, we use bobbin with 2 slots, transformer bobbin with 2 slots to separate the primary and secondary winding. In this way, we achieve highest isolation voltage, as well as minimize the isolation capacitance. As you can see in this design, we are able to achieve a interwinding capacitance of less than 1 picofarad. So here we are showing the performance of this reference design board. As we can see, we're achieving pretty good load regulation on all 3 output rails. We're also achieving over 75% efficiency at a 5-watt load. Here comes some waveforms we measured on the reference design board. On the left-hand side, we are showing the switch node waveform and transformer current waveform of the LLC topology. As you can see, the switch node waveform is very clean and achieving source switching. As compared to a conventional flyback on the right, the switch node waveform is showing a lot of voltage spikes and ringing when the switch turns off, as I explained in the earlier slides. Here I'm showing, on the left, I'm showing the input voltage waveform of the LLC topology. As we can see, the input waveform shows very little noise, only some voltage ripples. But as compared to a competitor flyback design, the input voltage waveform shows great amount of voltage, ringing, and noise, which can pollute the input voltage rail.
Thanks, Dee, for going over the theory on how a resonant LLC transformer driver functions and providing a design example to be able to achieve 5 kV isolation while biasing 3 different silicon carbide FETs. MPS is invested in the electrification market with innovative solutions for onboard chargers, traction inverters, and charging stations with products such as isolated gate drivers, GaN drivers, and transformer driver bias supplies. Resonant LLC supplies are a great way for biasing either IGBTs or silicon carbide FETs to help increase power density in next generation OBC and traction inverter designs over traditional flyback with better performance and space and cost savings in the designs themselves. Keep looking out for new products from MPS as we continue to invest in isolated products that will continue to push the envelope in electrification designs forward to achieve higher efficiency, higher power density, and smaller solution size. We are excited by the possibilities in the electrification market as adoption of electric vehicles has been increasing at an exponential rate worldwide, driven by regulations to achieve carbon neutrality. We'd like to thank Avnet Silica for putting together this electrification webinar and look forward to future events together. And thank you for taking the time to watch MPS onboard charger solutions today. Hope you guys all have a good day. Bye.